All right, so in this example problem, we're going to calculate the torque caused by each of these four forces, A, B, C, and D, about the pin joint at point P. And again, a pin joint is just a place that allows the system to rotate around. Let's say that each force is 100 newtons, and the distance between those vertical yellow marks on the rod are 12 centimeters each. So in order to calculate the torques of each of these objects, I'm going to bring back our torque equation. We know that torque, right, tau, is equal to R as our lever arm, multiplied by the perpendicular component of the force that is producing that torque. And so for each of these forces, I'm going to figure out how far away they are, what their R is from the pinpoint P, and then I'm going to find out the component that is perpendicular of that force if it indeed is at an angle, okay? So we know that each of these forces is 100 newtons, so I'll just go ahead and write that on my diagram. We know that each force, no matter how it's being applied, is going to be 100 newtons of strength, okay? And I know that the yellow lines are 12 centimeters apart. So I know that the lever arm, right, I'm going to call this RA, is going to be equal to 12 centimeters. Okay, so if I'm just looking at the torque produced by force A, that we can call that torque A, that would be force A perpendicular multiplied by RA. So the component of force A that is perpendicular multiplied by the lever arm, or the distance that force A is being applied from the pin joint. Well, I know that this force is completely perpendicular, right? There is no component of this force that is not perpendicular. So I can use the whole force as it is. So I know the torque produced by force A is just going to be equal to 100 newtons, that's the force, multiplied by 12 centimeters. And so that'll be 1,200 Newton times a centimeter. And it's okay that I'm using centimeters here. There's no standard unit for torque, so I could convert that to meters if I wanted to by dividing by 100, but I'll leave it as is for now. All right, the last thing I need to do for torque A is just decide whether or not that torque should be positive or negative. Like we just saw in the previous slide, if force A were the only force acting on this rod, it would cause this whole system to rotate like this, right? Counterclockwise, start to go in that direction. So because that's counterclockwise, that's going to be a positive. So I'm just going to put a positive sign in here. That's going to be positive 1,200 newtons times centimeters. So I make sure that I know that that torque is positive because of the way I've defined my system. Now let's take a look at force B. So I know that, again, the torque produced by force B is going to be equal to the component of force B that is perpendicular to the lever arm or the door, multiplied by the lever arm for, or how far force B is being applied. So in this case, I'm going to say that the lever arm for force B, or the distance from the pin joint, this RB, is going to be equal to, that would be, this is 12 right here, and this is another 12. They're each 12 centimeters apart, so that's going to be 24 centimeters in total from point P. Okay. Now, force B is at an angle, so I can't use 100 newtons. I need to figure out how much of force B is perpendicular to the door. I'm going to split force B up into two components, and I'll show those in blue. So if I draw a dashed line, I'll actually show this in a different color. I'll use green. If I draw a dashed line here to represent it's going to be the parallel component, right? This is the FB parallel because it's parallel to the door. And then I'm going to draw this line in here. This is going to be my FB perpendicular. That's the one I want, right? This is what I'm looking for. I can see here that in order to calculate that component that is perpendicular, I can take this 30 degrees, and this 30 degrees right here is this angle, okay? So what should I use, sine or cosine? Well, because the side that I'm looking for is adjacent to the angle that I've been given in this problem, I'm going to use cosine in order to solve for the component that is perpendicular. So I know that this is going to be equal to, right, FB cosine of 30 degrees. Once again, I'm not using sine here because the angle I was given is such that the component that is perpendicular is the adjacent side of the triangle that I've drawn. So be very careful about which trigonometric function you're using. So I'll go ahead and just plug those in. That means the torque produced by force B is going to be equal to Force B is 100 newtons, so 100 newtons times cosine 30 degrees. Right? That is going to be this whole thing is my FB perpendicular, multiplied by my lever arm, which again was 24 centimeters. And so the torque produced by force B will be equal to about 2,078 Newton times centimeters. And now I've got to be careful here because I need to consider the sign of this torque before I proceed any further. So I'll leave some room here in case we have a negative sign. What sign should the torque produced by force B be? Well, if I look at force B alone, what direction would force B only cause the system to rotate in? Right? You can imagine that if force B were the only force, I can look at that component that's perpendicular to help. This force right here would cause it to rotate in this orientation. Well, that's going to be clockwise, so that's going to be a negative direction. So the torque produced by force B is negative 2,078. Negative because force B alone would cause this to rotate in the clockwise direction. All right, now for force C, we can do something very similar. We know that the torque produced by force C is going to be equal to the component of force C that is perpendicular to the lever arm multiplied by the lever arm for point C. And in this case, since that's another 12 centimeters, I know that from the point P all the way over here to force C, that this RC here is going to be, I'll just write this over here, RC is going to be 36 centimeters because I'm 36 centimeters away from the origin in this case, or point P. Okay, and if I draw a triangle, just like I've drawn for force B, the components of force C would look like this. This would be the FC parallel because it's parallel to the door, and this would be the component of the force FC perpendicular. That's the perpendicular part that forms a right angle right here, just like this one did in the previous force. And so this is the only component that's actually responsible for producing a torque. All right, and once again, if I look at the angle that I've been given in this problem, the angle that I've been given is 45 degrees, and it happens to be adjacent to the component that is perpendicular. So I'll use cosine again. Now, we also know that if this angle is 45 degrees, then this angle also has to be 45 degrees. So it doesn't actually matter if you use sine or cosine here because they end up being the same. But just know that it's because we can use either angle. In this case, this triangle has two angles of equal value. And so my torque produced by force C is going to be equal to 100 newtons, that's the force, multiplied by, I'll just use cosine again, cosine of 45 degrees. Once again, you could have used sine because of the way the triangle was set up, multiplied by my lever arm here, 36 centimeters. So the torque produced by force C is going to be equal to about 2,546 Newton times centimeter. And once again, what direction is this torque going to have? Is it going to be positive or is it going to be negative? Well, if I look at the component of force here that is perpendicular, it's going to cause the system to rotate in this, I'll just show an arrow here, in that direction. And that's going to be counterclockwise. So I know this is going to be a positive torque. So I'll say that's a positive 2,546. And in this problem, both of the angles I was given just happened to use cosine. But just again, please know that it's never always sine or cosine when you're solving for torque. You have to think about the component of force that is perpendicular to the torque. So please avoid falling into a trap of thinking that it's always sine or always cosine. Now, let's take a look at force D. Force D is actually a bit interesting. Force D is being applied directly at the end of the pin joint, and it's pointing against the pin joint. So if I think about this, right, I can take a look at this is going to be another 12 centimeters. So the lever arm all the way to point D is going to be 48 centimeters, okay? So I am applying the force away from the center, right? In order to have a torque, there are two things you have to do, right? One, apply the force away from the center. In other words, your lever arm can't be zero, because if your lever arm is zero, you don't have any torque. But the second thing I have to do is have some perpendicular component. If I don't have any component of force that is perpendicular to the lever arm, then I'm not going to have a torque. And remember, the lever arm it's not really the door or the rod itself, but it's this line. I'm going to draw an imaginary line going through the pin joint. So right here, I'm going to draw this in red. Imagine a line going all the way through the center, right? This is my lever arm, right? This is kind of where it stops. So what's perpendicular to that line? Well, anything going like this is going to be perpendicular. But how about force D? Is force D perpendicular? No. Force D is pointing, in a sense, force D is parallel, right? This is parallel to R. It's not perpendicular. So because there's no component of force, right, FD perpendicular is equal to 0. There isn't any. Force D is not perpendicular. Then the torque produced by D is going to be 0. There is no torque produced by force D because it's pointing in such a direction that is not perpendicular to the lever arm. So imagine trying to move a door and you push on the edge of the door towards the hinge. Is anything going to happen? No, it's not going to happen. Yes, you're applying a force, but are you applying a torque? No. Is it going to cause the door to rotate? No. Okay. So I just want to make that clear. You got to keep track of two things for there to be torque. One, you have to have some lever arm that's positive. You have to have some lever arm more than 0. Can't be applied at the hinge. Okay, so if I apply force right here, not going to happen. Not going to do anything. And it has to be perpendicular to the lever arm. So it has to be at a right angle, or some part of it at least has to form a right angle with the lever arm itself. All right, so this is an example problem of solving for multiple torques. Please take a look at Canvas for some additional practice problems to apply this idea of torque, lever arm, and force.